Hello, today's episode is on momentum and impulse. This is a new unit, so we're going to look at a number of new topics. Today's topics are about calculating momentum, treating momentum as a vector, and also impulse. Impulse is going to be the change in momentum, and looking at force time graphs and how that relates to momentum and impulse. First off, all moving objects have a momentum. Officially, the formula is P is equal to the mass of the object times the velocity of the object. Notice the vector bars on these. Okay, momentum, yes, we're using the letter P. Don't ask me why. It's probably a French thing. But P is equal to the mass times the velocity. Okay, so that means that momentum is proportional to an object's speed, and momentum is proportional to an object's mass. The units for momentum, there aren't any units for it. Okay, so we're going to just leave it as kilograms for the mass times meters per second for the velocity. In the past, I've assigned a student's name to that, but I'll leave that up to you guys. So, sample problem 1. Okay, a train has a mass of 2,500 kilograms and is moving at a rate of 5 meters per second. What is the train's momentum? Okay, first, P is equal to the mass times the velocity. So in this case, the mass is 2,500 kilograms. And the velocity is 5 meters per second. Multiply them, and we get 12,500 kilograms times meters per second. Easy enough. Now, it is important to realize that momentum is a vector. If we define a direction as positive, then an object with a negative velocity has a negative momentum. For example, if I defined the rightward direction as positive, and a ball is going in that direction, hits a wall, initially it has a positive velocity, and therefore its momentum is positive. After it bounces back off the wall, okay, at this point my velocity is negative, and therefore my momentum is going to be negative. Let's look at a sample problem there. Okay, a ping pong ball with a mass of 3 grams is thrown downwards. Just before bouncing, it has a velocity of 8 meters per second downwards. Immediately after bouncing, it has a velocity of 7 meters per second upwards. Calculate the ball's momentum before and after bouncing. Then calculate the change in the ball's momentum. Okay, first off, let's draw a picture. Okay, here's the floor. Here's our ping pong ball. It's going down, and at this point, it has a velocity of 8 meters per second. Okay, afterwards, it bounces back up, and in this case, it has a velocity of 7 meters per second upwards. So, the change in momentum is equal to the final minus the initial, or in this case, 0.003, that's 3 grams in kilograms. Okay, and it starts off with a velocity of 7 minus, okay, negative 8. Okay, so in this case, which way have I defined to be the positive direction, and which way is the negative direction? Okay, obviously, the 7 was positive, so therefore up is the positive direction, exactly what we're used to. So the change is 0.045 kilograms times meters per second. Okay. Whenever we see these problems, don't forget negative direction means negative velocity, means negative momentum. Pay attention to your signs and read the problems closely. Okay, the next topic we're going to deal with is impulse. Impulse is the change in an object's momentum, just exactly like the problem we saw earlier. Okay, impulse, we're going to use the letter J for impulse. Again, don't ask me why it's J. I always blame the French for these things. Okay, but the letter J is what we're going to use for impulse. And J is equal to the change in your momentum, delta P. Or since mass is generally constant, that's going to equal m times delta V. Notice the vector symbols again. Okay, pay special attention when the direction of velocity changes. Make sure you choose one direction to be positive, the other direction is negative. Impulse is also the average force F that is applied over a time t. Okay, in formula form, the average force times time, that's also going to equal mass times the change in velocity. We're actually going to use the second half. Okay, we're not going to use the J all that often, but it's important to know that the average force times time is equal to the mass times the change in velocity. Okay, the T is especially important, okay, because if I can increase the time, then I can reduce the force. This is especially useful for stuntmen, airbags. Spread the time that it takes for a stuntman that falls from a maximum velocity all the way down to 0. Okay, by increasing the time, it has less force. Stuntman doesn't go splat. Okay, same thing for the airbag in your car. Okay, if you're forced to use it, the airbag deploys and it spreads the time for your body to come to a complete stop and decreases the force that your body experiences. Okay, so let's look at a sample problem. Okay, here I have my cow up in the upper corner, and a train has a mass of 2,500 kilograms and is moving at a rate of 5 meters per second when the engineer slams on the brakes because he spots a male cow. That belongs to Dora on the tracks. Okay, I'll skip the pun. If the train takes 12 seconds to come to a complete stop, what average force is applied by the brakes? Well, let's look. Okay, impulse is equal to force times time is equal to change in momentum. We know our momentum before was 12,500. Okay, since it comes to complete stop, subtract 0, and my force times 12 seconds, and then force is a little bit over 1,000 newtons. Okay. So it takes the brakes basically apply a little over 1,000 newtons to stop this train. Okay? So let's look at a force time graph. Not all forces are even. Okay, they're applied over different time periods. Think of the springs. Think of a ball bouncing as it hits the ground and compresses and then comes back up. Okay, the force is not a constant. Okay, so if we're given a force time graph, impulse is going to be the area under the curve. We've seen that in a number of situations. From a velocity time graph, we got position. Earlier in the previous unit, on a force distance graph, the area under is work. In this case, for a force time graph, always double check your axes, okay? Make sure it says force and time. Okay, and when I multiply it, newtons times seconds, that gives me impulse or momentum, because this also is equal to kilograms times meters per second. Okay, for those of you with a calculus knowledge, okay, impulse is going to be the integral of f of t dt. Okay, thank you very much.